Oh. I don't know about anybody else, but I can't actually hear any sound.
We can't hear. Maybe you need to enable the volume.
No sound, yes.
Enable computer sound, something like that while sharing.
Thank you for taking your time and coming to my presentation. Let me introduce myself. I am Dilip Ajay, working as staff engineer at Qualcomm Ireland. I am involved in physical design of analog mixed signal IPs. Primarily, all my prior papers and patents are in the area of prediction and mitigation of physical design problems at synthesis stage. My current talk is also focused in the same lines. Today, I will be talking about my paper called Bit Density Based Pre-characterization of RAM cells for Area Critical SOC Design. So as I move along my presentation, I will be focusing on these subjects. So after spending considerable amount of time in physical design domain, I have seen what we designers primarily focus right after synthesis is how do we get from this picture to this. That is, we immediately start thinking about placing the physical objects like pins, memory cells, hard macros, etc. in hand in a way that we get unblocked core area, place objects in a way that we do not have congestion, meet timing and other metrics. However, very few think if the memory cells chosen is really best suitable for the design. Do we have a way to come to this conclusion? Is there a scope to save more area by picking right memory cells? The more we ask questions, the more we think of innovative ideas. So what are we solving? We know that memories today constitute a significant percentage of almost all SOCs die area. Now for a given logical depth, which is the address, the given logical width, which is the data bits, and cycle time requirement, we get many memory configurations after memory compilation with different values for access time. Access time can be is the same as the clock to queue time in the registers, physical width, physical depth, and area, like we see in this table. Today, the decision to pick the right RAM cell for a given design is iterative and manual. Mostly the decision is random and are taken by logic designers who, with all due respect, do not much care about the physical design issues at this stage. Physical designers encounter issues very late in the design. Sometimes we see that the die area isn't enough to fit the memory cells. Sometimes we do not encounter any issue at all. But we never think in this scenario if there existed a scope to save more area and thereby save more power, etc. Existing techniques for this mostly involve designer feedback, which is a slow, reactive, and incremental approach. Let me now talk about my idea in detail. In a nutshell, my key idea is that we score each RAM cells in the library based on its area characteristics. This is a one-time processing effort before the synthesis flow. Now, multiple scores are possible per library cell for the range of expected values for different parameters available during memory compilation. The library cell score for area optimization is then used in the synthesis flow. Now the pre-characterization scores are used to estimate and optimize the area profile. So what is the scoring scheme for RAM cells? Let me introduce something called Area Difficulty Score, ADS, for a RAM cell. Now it is a parameter or simply a weight given to each RAM cell of the library based on how much each RAM cell is likely to contribute towards the area. Area difficulty score of each RAM cell is thereby a function of number of words, number of bits, its physical area or physical width into depth, And mathematically, we can represent the same as a function of words bit geometry x and geometry y, as shown in equation 1. Area difficulty score of a RAM cell is directly proportional to a new parameter I'm introducing called megabits per millimeter square, which is nothing but its density, bit density, which will determine the area efficiency of each RAM cell. We can imagine this as an analogy, same as any density parameter in real world. So how do we calculate megabits per millimeter square? It's very straightforward and simple. Area of RAM cell in millimeter square is its physical area, which is length into breadth, divided by 10 to the power of 6, like shown in equation 2. And megabits is words into bits divided by this number, as shown in equation 3. Therefore, megabits per millimeter square we can derive by dividing equation 3 by equation 2. Okay, so area difficulty score is directly proportional to 1 by AT, or inversely proportional to AT, where AT is the access time of RAM cell. AT, as discussed, is the time it takes from clock to queue of the memory cell. So how can we fit this idea in current synthesis flow? So you can see this chart. Basically, there are two additional steps which we are introducing in the traditional synthesis flow. One, we provide bit density aware pre-characterized RAM cell library. And two, we provide a memory.txt file which has all the important information about the memories used in your block. So you can see the input to any synthesis flow is a very long or a high level description, the technology files, the boundary constraints or the timing constraints. Along with that, we are also providing memory.txt file and bit density based RAM cell library. So that is a new thing for the current synthesis flow. Now, let's establish the idea with an example to absorb everything I spoke so far. Let's take a case where the architectural requirement from the spec for the memory used in the module is to meet logic depth or address of approximately 21.k bits and logical width or data of 266 bits. And this is kind of a very standard case in most of the network chips that we design. Now, in each write cycle, we need to write 160 bytes of data into 3 banks of memory. That's our requirement. And the aspect ratio of the block, say, is 5,000 micron into 1650 micron, where X is 5,000 and Y is 1650 micron. A very standard block size that we get in SOC or in, say, different network chips that we design. Now, with the new pre-characterized RAM cell library after memory compilation, we will see new parameters defined in them. It will look like this table. Now, you can see there are n configuration for one type of memory cell, just like we had before. However, what's new is we have a metric which can be used to determine the best memory suitable for a given design. Since the synthesis tool is physically aware, it can read the size of the module. The synthesis tool can now easily pick the memory configuration with highest megabits per millimeter square, which would otherwise be user input based on floor planning results, and it can be iterative. So this is how the new memory compilation results will look like. So content of memory.txt file. This file mainly contains which memory cell type is to be picked to meet the logical requirement. We then specify all of the important details like the physical width, physical depth, mux factor, number of banks, etc. based on highest value of megabits per millimeter square from the pre-characterized library. Now, if you see the one highlighted in yellow here, the physical depth is 16,384, width is 74, banks 8, mux factor 8, and number of repair column is 2, pipeline is external, logical width is 266, and logical depth is 21,504. So all these numbers, I took it from the pre-characterized, RAM cell library that we have after memory compilation. So if you see what is there in the green, those numbers are exactly same as the one mentioned in the memory.txt file. Now, floor plan inputs. Since we need to write 160 bytes, which is 1280 bits of data in each cycle, into 3 banks, we can see that we would need 4 instances of each RAM cell selected to realize logic depth of 21K approximately and logic width of 266 bits, which comprises of 256 bits of data, 10 bits of error correction logic, plus 2 repair columns. Therefore, we would need 5 into 4 instances to realize a logic width of 1280 bits or 160 bytes. Since we need to write 160 bytes of data in 3 banks, the total instances needed for this module to meet the aspect ratio and logical requirement would be 60 instances. Now that's the mathematics usually we physical design engineers do before floor planning. So this is how the final floor plan picture will look like for this example. Now from this picture we can see that we are able to place all the memory instances in an order that keeps in mind the channel width, space for interface logic, etc., and still meet the requirement. Now this is an idea which is still to be proved with real test cases and is at very crude level as of now. I'm afraid I cannot present real figures on how much turnaround time one could save or how much area one could save on multiple designs, etc. But I'm convinced it is beginning of a whole new world for EDA companies to think, and I think that's the way forward. So let's look at this final floor plan picture, closely. You will see that each memory instance X and Y is defined there. It's 461.385 and Y is 262.32. So if you do your mathematics for 60 instances placed here, along with the channel space and interface logic space, still you will be able to fit into the aspect ratio of the block. And you can also see neatly we can arrange the memory instances in a way that the 160 bytes can go into these memories. So let me conclude. A new approach is proposed which can easily be integrated into existing physical aware synthesis tool. The pre-characterized RAM cell based on bit density aids synthesis tool during technology mapping step to intelligently select the best RAM cell for the given module for the aspect ratio and logical requirements, which would otherwise be iterative and error prone, saving a lot of turnaround time. So I will pause here and open the forum for questions. Thank you.
Thank you very much indeed. Dilip is, I hope, online and able to hear us as well.
Yeah.
Excellent. Do we have some questions? Oh, stunned silence. Is that because everybody is on mute?
Looks like they understood it well.
Yeah, I'm not absolutely sure.
So I asked a question in chat window maybe. Dilip, do you think that this will be implemented in EDA tools, and what will be the approach to start with?
I mean, we can take small test cases in the beginning and start this flow in the synthesis existing synthesis tool and see how it works out. I mean, one best approach EDA companies can come up is they can collaborate with companies like Qualcomm and certainly we can kind of kickstart with the existing flowchart and algorithm we have in hand and see how we can compile the memories and get more real data into picture and come up with the strategy.
Are you engaged with EDA companies at the moment on this?
No, as of now, this is purely my idea, but I think I'm trying, I would love to, in fact, engage in future, but we have our own CAD team inside Qualcomm to begin with. So as time, once I have the time, I mean, I will certainly would love to work with the CAD team to get this into our flow. And in future, maybe if we needed, we have Cadence also coming to Qualcomm. So yeah.
Thank you.
I've now just seen your message, Summit, in the chat. Are there any other questions? It sounds like a call is going out from Dilip to the EDA community to try and make this happen.
Sure.
If we have no other questions, then we can finish this session early, which is remarkable. And I would encourage everybody, including the presenters, to go into the virtual conference rooms, where we can hopefully continue the discussion. They're open. You don't even need to register, though obviously if you do, you can change your avatar and do all sorts of fun things. I will try and put a message in the chat window. Oh, hang on, I think that's gone to everyone publicly. There you go. So if you hadn't already got the link, then that link is there in the chat window. So I encourage everybody to go there to continue the discussions. Thank you very much indeed for participating in this first session, and I'm sorry that technically we had a few entertaining challenges.
Thanks a lot, Mark. Talk to you later then. Bye-bye.
Thank you very much, everybody. Cheerio, bye.